Hello young little minds, welcome to another session of All 4 C Learning program. Anna, I am DNR, your physics lecturer. We are doing with the 12th class second chapter, electric potential and capacitors, right? So in this one, we have till date we have completed about capacitor, types of capacitor, series parallel combination of capacitor, energy stored in capacitor, the effect of the dielectric of the capacitor, all these we have dealt. Now today we will take up the concept of common potential. What is common potential? How do you calculate the common potential of a capacitance? All that we will understand, all those things, okay, right? So before going to that, let's have a recall of what are the basic things that are required to understand the today's concept, right? So I was telling you, capacitor is a device to store charge and electrical energy. It stores electrical potential energy, right? Well, capacity of a capacitor, the ability to store is capacitance. How much does it store? The measure, the capacity of a capacitor is called capacitance, given as C is equal to Q by V. Right, the amount of charge stored per unit potential. So from this I can write CQ is equal to CV or V is equal to Q by C. The potential is charge per capacity. V is Q by C. This is the formula. Later I've given you the units, the dimensional formula, all those things, right? Later we have dealt with a simple spherical capacitor sphere 4 pi epsilon naught R. But you know, its size is big but the capacity is less. But we don't want, we wanted to have a more capacity in smaller size. So for that we have condensed. It was a condenser, right? A spherical condenser, a parallel condenser, cylindrical condenser. But now all these condensers, there are no simple capacitors. All these condensers are in use. So we call these things as, itself as capacitors. So a spherical capacitor, combination of two spheres, concentric spheres. Parallel plate capacitor, combination of two parallel plates separated by a small distance. Cylindrical capacitor, two concentric cylindrical hollow cylinders, right? So that way we have even dealt with the formula also. Then energy stored in a capacitor, energy. You know, suppose I was telling you while defining the charge, the capacity of a capacitor, the charge stored in a capacitor and potential V, the charge and potential. If you draw a graph between charge and potential, for a capacitor, charge Q directly proportional to potential. Well, Q is equal to CV, where C is called the capacitor of the capacitor or the capacitance. If I draw a graph between Q and V, it represents a straight line for a particular capacitor. A straight line passing through the origin. Well, if this is theta, the slope of the line, slope is tan theta, right? This is in the form of y is equal to mx. Y-axis charge Q, x-axis potential. So m is slope, C capacity. So the slope is the capacity. When you draw a graph between Q and V, charge and potential, the graph is a straight line passing through the origin. Y is equal to, right? It's a straight line passing through the origin. So like y is equal to mx. Well, y-axis charge, x-axis potential. So y is mx, m is c, slope is c, tan theta, right? Now if you find the area of this graph, if you take the area of the graph, now look. So what is the area of the graph there? Now this is starting from 0. So this is V and this is Q. So the area of the graph, if I take down, so it's a triangle, it's half base into height. Base is V0, height is Q0. So it's Q0, V0. So it's half Q0, V0. This is nothing but the energy stored in a capacitor. So when I draw a graph between charge and potential for a particular capacitor, it's a straight line passing through the origin. It is like y is equal to mx. So when I take the formula for the charge, Q is equal to CV. C is the slope, capacity, tan theta. C represents the slope, that is tan theta. Now if I take the area of this graph, it is a triangle, half base into height. Base is V0, height Q0, so half Q0 V0. The area of the triangle. So the area of this graph represents the energy stored the energy stored in a capacitor, half QV. Well, the energy stored is half QV, half QV you can write. The energy stored in a capacitor is half QV, or it is half CV square, or it is Q square by 2C. Energy stored. Later we have dealt with the effect of the dielectric. Whenever a dielectric is placed between the plates of the capacitor, then this will reduce the potential. Hence the capacitor increases cadence. The potential has gone down. So this way it is. Now let us understand the concept of common potential. Now what do you mean common potential? Let us consider two capacitors like this. Let's take two capacitors this way. Now look. Suppose that there is a capacitor C1. This is a capacitor C1. It is charged to a potential V1. Well, the charge stored on it is Q1. And the energy stored in it is U1. Right? So, consider a capacitor charge. Consider a capacitor C1. Let it be charged to a potential V1 by a source battery. Then to a charge, the charge stored in it is Q1 and the energy stored is U1. Then we know. So according to the definition, C is equal to Q by V, Q. So the charge Q1 is, the charge Q1 is equal to the charge stored. So the charge stored Q1 is C1 into V1. And the energy stored, it is half C1 V1 square. Right? You can write half C1 V1 square or Q square by 2C or half QV. Anything. Let this be equation 1. Well, consider another capacitor. Let's suppose there is another capacitor C2 charged to a potential V2 with a charge Q2. The charge stored on it is Q2 and the energy stored is U2. Right? The energy stored is U2. Now, in this one, the charge stored is Q2, that is C2 V2 by definition, and the energy stored U2 is half C2 V2 square. This is equation 2. Now, both capacitors are actually charged separately. Now, this is charged separately with some source V1. It is connected to the battery. Switch on the battery, the charge goes on. The potential is V1. Now, this is another capacitor connected to another battery. It is connected to another battery. It is charged with potential V2. Charge is Q2 like this. Separately, they are charged and they are disconnected, separated, isolated. They are isolated with their respective sources. Right? There is no connection now. Separate capacitors. Now, combining these two, the total charge that is stored in these two capacitors, the total charge stored in the capacitors, the total charge QT is Q1 plus Q2. Well, the total charge is Q1, that is C1 V1 plus C2 V2. Similarly, the total energy stored, the total initial energy stored, that is U total is U1 plus U2. So that is U total is half C1 V1 square plus half C2 V2 square. Let this be equation 3, this be equation 4. Right? So this way, consider two capacitors, C1, C2. Let them be charged separately, individually with separate sources to respective potentials V1, V2. They are charged separately with their respective sources V1 and V2. Let the charge stored in them be Q1 and Q2. And the energy that is stored is U1 and U2. Separately. Both are separate. Then Q1 is C1 V1, U1 is half C1 V1 square. Well, Q2 is C2 V2, U2 is half C2 V2 square. Together, of course, even though they are made to charge separately, now together, put together, the total charge in them is electrically the total charge is Q1 plus Q2. Combined charge, C1 V1, C2. The total energy is this. right? You remember this. Now what I am going to do is, now I am going to connect these two capacitors, combine them, join them electrically. You call it as biasing, electrical bias. I am putting them in connection. So electrically, if I bias them in connection, I am making the connection between them, right? I am joining them, I am combining them electrically. How you can do? Well, suppose if this is one capacitor positive negative, this is another capacitor positive negative, I can combine plus to plus, minus to minus like this. This is one way of connection, the correct way of connection. Both are connected in the right way. I can even do the other way also, plus connected to minus, minus connected to plus. Right? We have to deal with it, both the cases there. Both we have to consider. So what happens if I connect positive to positive, plus is connected to plus and minus is connected to minus. Well, both are connected. There are two keys like this. I switch on this key and this key. Then what happens? Right? Both are connected. You see, in the earlier chapter, electric charges and fields, in the starting part of the chapter, there we have dealt with a topic called charging of electrification, the charging of any body, giving charge to a body. The process of giving charge to a body was called as electrification. There were actually three standard methods, but actually overall there are several methods, but three standard methods. One is charging by friction, second charging by conduction, third charging by induction. The second method, charging by conduction method. You please recall what we were doing. Charging by conduction method. So what we were doing is, there was already existing charge body. There was a body already possessing charge, some charge. And to this charged body, I was connecting another uncharged body, directly or indirectly, and transfer the charge from one body to another body. I was transferring the charge, making the uncharged body get charged from a already charged body. By connecting them by means of a conductor, either directly putting them in contact or connecting them by a wire, direct or indirect contact. So with an already existing charge body, I am giving this charge, some part of this charge, to another body by making a connection, electrical connection. Then the charge is shared. So the already existing charge body will give some part of the charge to it, and already the charge, total charge that was existing, is shared between them. Until both the charge is shared until their potentials are equal. Can you recall? Could you recall? Right? So already there was a charge and there was an uncharged body, both are put together. Now the charge is sent until their potentials are equal. Now that was common potential there. Well, charge moves from one body to another body. Charging of the body from one to another takes place until both attain same potential. Common potential. Even our concept is the same. We have dealt with this there. Same thing we are doing but with capacitors we are doing so. Even I have given you an example also. Then when I was explaining the concept also, I gave an example. Consider a tank with some water already existing, it's fully filled. Consider another tank, well, with empty tank with no water. So a tank is like a body which is storing water, a capacitor. There is another tank, empty. Now we were connecting both by a pipe at the lowest point. So there is a connection. Now the water flows from one tank, from the tank where it was existing in high level. Now it will flow from this to this until their levels are equal. The same concept we have applied there, and the same thing take place even here also. It is the same method by which you are going to explain it. Actually, a capacitor is like a tank. So there is a tank, you have poured some water like charge to a level that is potential V1. So you store some energy V1. Similarly, another tank C2, charge Q2, potential V2, energy U2. Now both are connected, biased. Then what happens? So now there are two tanks with some little water in them. There is some water in this and this. the levels are different. Now make a connection. So what happens? The liquid will flow from the tank with higher level to the tank with lower level until their levels are equal. Similarly here also, this is a tank with charge, right? It's a capacitor like tank storing charge like water with a potential level, electric level and the energy. This is another one. Now both are made connection, where both are connected. So what happens now? The charge will flow. As water has flown from higher level to lower level, similarly the charge will flow from high electric level to low electric level. Well, the electric level is referred as potential. So the charge flows from the higher electric potential to lower electric potential. So from high potential to low potential until their levels become equal. That is, the potentials become equal. And that potential is called common potential. So what happens? That the capacitor with more potential, higher potential, it will let some charge to move away. The capacitor with low potential takes the charge, and this will increase its potential. So the potential difference that was there, now it is averaged, like so the both level gets equal. So both attain a common level, and that common level is termed as common potential. Well, after the connection is being made like this, then some charge will move from higher potential to lower potential. One capacitor will lose charge, other capacitor gains charge. Obviously, water will flow from tank with more level to tank with lower level until their levels are equal. So one tank will lose water, other tank will gain water. So similarly, the charge flows from one capacitor loses, the other one gains. So what happens? There is some redistribution of charge, rearrangement of the charge take place, right? So now after the connection is being made, the charge on this one is no more Q1, let it be Q1 dash, right? And the energy is U1 dash. Similarly, charge on the second one is Q2 dash and the energy is U2 dash. But this redistribution and rearrangement of the charge take place until their levels become equal. That is potentially equal. So both attain same potential, and let that potential be called as common potential Vc. So after the connection is being made, both attain a common potential. This is Vc. Both will attain a common potential Vc. Now the potential of this one is Vc and this one is Vc. Correct? Now, so these are all the parameters before the connection is made. So let us put it as before common potential. This is all before connection. Before both are electrically connected. Initial, right? This is initial charge, initial energy, total initial. So this is total charge initial. This is initial charge. Before connection. Here also total initial energy it is before connection. So these are all the parameters before the connection is made. Now after the connection is being made, so after connection, I mean final. Now after the connection is being made, final. Now coming to the first capacitor, the charge in it is Q1 dash. Well, according to the definition, C is equal to Q by V, Q is equal to C. So Q1 dash is C1, capacity remains same, C1, and the potential is Vc. Now energy, U1 dash, half C1 Vc square. Similarly, second one, for the second, this is for the first capacitor. Now for the second capacitor, second capacitor, right? Q2 dash, it's C2 Vc, and energy U2 dash, half C2 Vc square. Now combining these both, the total final charge, that was total charge initial. Now the total final charge Qt dash. So Q1 dash plus Q2 dash. This is Q1 dash plus Q2 dash. So Qt dash is equal to C1 Vc and C2 Vc. C1 Vc plus C2 Vc. Well, it is C1 plus C2 into Vc. This is C1, V1, this is initial, this is final. But you know, at that time when I was explaining the concept of conduction, I was telling you, right, I said when the conduction takes place, right, whatever be the process, I said while explaining the properties of the charge, you know, a electric charge, the very first topic of the electric charge and fields, the basic fundamental property of the charge is charge can neither be created nor destroyed, energy is conserved. So charge is conserved. So according to law of conservation of charge, the charge is always conserved. That is, the charge always remains constant unless it is either transmitted, transported or added, or removed or added there. Right? So charge is conserved. So therefore total initial charge in both the capacitors, total initial charge in both the capacitors is total final charge in them. So total initial charge before and total final charge final, right? Initial and final charge both same. So the total initial charge is equal to total final charge. The total initial charge is Q1 plus Q2. The total charge is Q1 plus Q2 and the total final charge is Q1 dash plus Q2 dash. So that is C1 V1 plus C2 V2 is C1 Vc plus C2 Vc here. But here Vc is common, so I shall write it as C1 plus C2 into Vc. Get it down. So when I get that down here, I get equating both, I get the common potential. So the common potential is equal to the common potential Vc is C1 V1 plus C2 V2 by C1 plus C2. This is the formula. The common potential is C1 V1 plus C2 V2 by C1 plus C2, the common potential. And now the final energy is half C1 plus C2 into Vc square. Now substitute this here, you will get the final energy that is stored. Now in this process, well, charge is conserved, but the energy, some of the energy is lost. Charge will be totally conserved, but the energy, initial energy and final energy both are not equal. Some of the energy is lost. The energy that is lost in the form of heat, energy lost in the form of heat. Now this is given by the formula half C1 C2 by C1 plus C2 into V1 minus V2 whole square. The final energy stored is less than the initial energy. Some of the energy is lost. This is less than the initial. So the energy that is lost in the process of conduction process. Half C1 C2 by C1 plus C2 into V1 minus V2 whole square. This is the energy that is lost, right, in the form of heat in the form of heat. Now this is the common potential of the system of charges there, right? C1 V1 plus C2 V2 by C1 plus C2, and this is the totally lost. The final energy is this. Substitute Vc in this one, you will get the final energy there. Okay, right? So this way you find out the common potential of the system. Thank you.